Is Zachary from UC Riverside.
So good morning, everybody. Thank you for coming today. My name is Zachary Benavides, and I'm very happy to be here today to present my paper to you, DProf, a distributed profiler with strong guarantees. This is work that I did while I was a PhD student at UC Riverside with my colleague Keval Vora, who's now a professor at Simon Fraser University, and my advisor, Rajiv Gupta. So the outline for my talk today, I'll start off by telling you a little bit about what DProf is and the goals that it tries to accomplish. And then I'll talk to you about one of the core components of DProf, which is called Freezer, which is a new algorithm for solving the timestamp synchronization problem, which enables DProf to meet the goals that it set. Then I'll talk about two extensions to DProf that we wrote, DCSP and DCause. These are both distributed versions of existing shared memory parallel performance analysis techniques that we built on top of DProf. And then finally, I'll show you the results of a sort of holistic accuracy experiment that we did using DCSP and DCause to show the effectiveness of Freezer and DProf in relation to other current timestamp synchronization algorithms. Okay, so fundamentally DProf is a profiler for heterogeneous distributed systems. So it's a tool for investigating the performance of these types of systems. The input to DProf is basically a set of region-based annotations. So you go through your code and you mark the parts of your program that have semantic meaning or that you care to analyze in some way. So for instance, loop bodies or maybe specific statements or function calls. And the output of DProf is basically a set of traces, one for each thread in the distributed system, which mark the events that happened, in this case entrances and exits to these regions that you've defined. And they're time-stamped with synchronized timestamps that are directly comparable to each other. So it's as if you had a shared clock in the distributed system when you're doing your analysis. So when you use DProf to write an analysis, you can just kind of pretend that you had one clock everywhere. So the goals of DProf are twofold. So first, we want it to be extensible, sort of like a platform for rapid prototyping of new analyses that you want to write. And secondly, we want it to provide, strong error bounding. So this process of providing these synchronized timestamps is one that's not perfect. It has there's some error that gets introduced when you do this, and the unique thing about DProf is that it gives you strict bounds on how big that error can be. Okay, so the kind of magic sauce behind DProf is this new algorithm for the timestamp synchronization problem that we developed called Freezer. And the timestamp synchronization algorithm is essentially the problem of creating those synchronized timestamps. So if you have, so in a distributed system, you'll have several local clocks. In our case, we used one local clock for each thread. So for each, for each core, not each thread. The Intel timestamp counter, if any of you guys are familiar with that. And so before DProf does its work, the data that you have are these traces of timestamps which are unsynchronized. Timestamp synchronization takes those as input and then gives you traces which are synchronized. So as I mentioned before, DProf will return not point timestamps, but interval timestamps, which say, okay, the converted version of this timestamp is between 15 and 20, for instance, as opposed to just saying, okay, my guess is that this is 17, and then leaving you to, infer for yourself how close to correct that is. So the way Freezer works is by dividing this problem into two subproblems, which we call zero estimation and frequency estimation, and it does both of the estimators that we define here provide strong bounds on their estimates, and that's how we get strong bounds on the overall conversion. So zero estimation is essentially the problem of determining a pair of timestamps from two different clocks which correspond to the same moment in real time. And relative frequency estimation is essentially determining the ratio of the clock speeds. So the different clocks in your distributed system can in general have been started at different times because you don't boot the machines up all at the same time, and they could also run at different frequencies, even if they're on a machine that has the same nominal core speed. Okay, so this is basically how the zero estimation works. In this figure, we have two timelines for two threads in the system. The top one is for thread 1, the bottom one's for thread 2. So it's very simple. It starts off at thread 1 takes a timestamp, which we call x, and then sends a message to thread 2. Upon receipt, it takes a timestamp, which it calls y, and then sends a message back to thread 1, who takes a final third timestamp z. So the 0 here is this triple of timestamps x, y, z. And since these are all ordered via the communication that's going on here, we know that the true timestamp, the true converted version of y, lies between x and z. Make sense? Okay, so the relative frequency estimation basically does something very similar to the zero estimation. It basically performs zero estimation twice, separated by some amount of real time in between the taking of the zeros. So if you look at the timestamps which are connected via blue lines, and you look at the ratio x2 minus z1 over y2 minus y1, you can think of that ratio as an estimate for the relative frequency of these clocks, because each of the clocks is measuring the same interval of real time. But since we know that x2 minus z1 is smaller than y2 minus y1, we know that that's a lower bound. Similarly, if we look at the the timestamps connected by red lines, we can get the other half of the bound. Okay, so once we have the frequency and the zero calculated, the conversion is just this given by this simple transformation here. So if t is the timestamp we want to convert, and z is the local component of the zero, so it's the y here in this case, and f is the relative frequency, then what we do is we just subtract the local component of the zero from the timestamp we want to convert. That essentially gives us an interval, and then we perform, you can think of it as like a unit conversion from the units that the source clock measures to the units that the destination clock measures. That's what multiplying by f gives you. And then we add that back onto the corresponding remote part of the zero. Okay, so we do that for each timestamp in the thread, in the trace. So this is a little experiment we did to look at the performance of Freezer relative to other timestamp synchronization methods. So we compared against three other methods. Convex hull and linear regression are two of the oldest algorithms for solving the timestamp synchronization problem, and they remain to this day some of the most robust algorithms for it. They essentially work by taking the timestamps that you would have generated anyways as a result of performing your analysis, and they perform like some statistical procedures in order to estimate like a linear transformation from one clock base to the other. The AR convex hull method, which is this red line here on the top, is a restructuring of the convex hull method using linear programming that allows you to get strong error bounds. So the same type of thing that we're providing, the error bounds here, that's what the AR in this stands for, accuracy reporting convex hull. So the AR convex hull method is quite expensive. It will give you the bounds if you care about them, but it does so at a huge computational cost. Whereas Freezer is able to give you those bounds at a cost that's higher than convex hull and linear regression, but not by a whole lot. Okay, so the first extension that we wrote for DProf is called DCSP. So this is an adaptation of a method called context-sensitive parallel execution profiling, which we developed for profiling shared memory parallel programs. And what it essentially does is it gives you this kind of data structure that you see here, where you can look at it and you can say for any point in the execution of the program, what was every thread doing. So in the first part of this, both threads were in the loop body. Then in the second part, T1 was in the loop body while T2 was waiting at a barrier. And in the third part, they were both at a barrier. And then once you have this data structure, you can evaluate different queries over it in order to figure out performance, in order to find performance bugs and things like that. So this is an example of a CSP query that would find the duration of time that the program spent in a straggler state. So this is where all the threads but one are waiting in a barrier for one thread to finish their workload. So this can be indicative of workload imbalance in distributed programs. So it essentially says there exists a thread T such that for all threads U not equal to T, T is in the loop body and U is in the barrier. So we were able to essentially just drop in the timestamp synchronization, the results of the timestamp synchronization that Freezer gives us through DProf into our original implementation of CSPs, and it was pretty clean. That was a pretty easy one to do an extension of. The second extension that we made was called DCause. So causal profiling is another technique for shared memory systems, and it seeks to answer questions that are of the following form. So for instance, if I wanted to know if I speed this thread up by 20%, how much faster will my entire program be? Or if this function executes 5% faster, what will be the overall impact on the total execution time of my program? So we built a type of causal profiler for distributed systems using DProf. We take the output from DProf, the synchronized thread traces, and we build this sort of graph that you see here, where the vertices in the graph correspond to events like entering and exiting loops or beginning and ending send or receive operations, and the edges connect vertices which are causally related. So for instance, you have to enter a loop before you exit a loop, you have to begin a send operation before you end it. And then we classify the edges into two categories. So the red and black edges are edges that we call inelastic edges, and the blue edges are edges that we call elastic edges. The nomenclature here is because the blue edges are ones that we've decided can grow and shrink based on changes in other parts of the execution graph. So for instance, if I wanted to ask using DCause what would be the effect on the overall effect of eliminating this loop from the execution of thread 1, what it would do is it would go and it would find this red edge 5. It would reduce that to 0. And since the edge between the loop end and the send begin is inelastic, it would readjust the timestamps there to bring it back down to the same edge weight of 1. And so it would keep pulling these nodes back in time until it gets to the receive end, which it would pull back. And then it would see the receive begin, and it would not pull that back because that's an elastic edge. Its weight is allowed to change. So DCause basically takes as input which of these types of edges you want to relax and by how which of these types of edges you want to contract and by how much you want to contract them, and it constructs this graph and then does that type of pulling manipulation that I just described. This was a little bit more complicated than the last DCSP to implement, but still of pretty moderate complexity. This only took us a few days to get working. The trickiest part was just constructing the graph. Okay, so finally we used DCSP and DCause to do sort of a holistic accuracy evaluation of DProf with Freezer as opposed to other synchronization methods. So we started off by taking 3 programs under test, a connected components program, a PageRank program, and a k-means program. These were all running on a heterogeneous cluster that we built out of basically the machines that we just had in our lab. So that included like a file server and the machine that I used as my desktop machine, plus some compute servers that we had lying around. So all over the board kind of thing. So as a first step, we used DCSP to perform straggler analysis to try to find the stragglers in these programs. And in the table below, a higher percentage means more severe straggling, so more time was spent in a straggler state. And the interesting thing to note here is that Freezer gives us, you can see that we were able to propagate the bounds all the way to the end, the final result of this analysis, and Freezer gives us pretty tight bounds on what it believes to be the straggler score in this program. The other interesting thing to note here is that all 3 of these, depending on what timestamp synchronization method you use, are like pretty wildly different. So at most, one of these is correct. Okay, so in the second part, we used DCause to ask the question, what happens if we were to speed up the identified straggler by the straggler score that we calculated in the first part? So here we have two new entries in this table, one for linear regression with freezer straggler score and another for convex hull with freezer straggler score. And this was to sort of give these methods the benefit of the doubt of, just in case there was some systematic error or something introduced by freezer in the first step when calculating straggler scores, or by themselves for that matter, what happens if, on the analysis, if we essentially remove that source of error? How good will they be? So again, we see that there's vastly different estimates for each of these, and again, we see that freezer is pretty confident in its estimate. So finally, we implemented this optimization by removing the straggler that we injected into the programs, and we observed the actual speed up that was noticed. And from this, we can see that DProf using freezer was much more accurate in its prediction of the overall speed up of the program than if it used any of the other timestamp synchronization algorithms. Okay, so in conclusion, DProf is an extensible profiler for heterogeneous distributed systems, which uses a new timestamp synchronization algorithm called freezer to provide the strongly bounded analyses that it requires. We showed two examples of extensions to DProf, DCause and DCSP, and we used them to evaluate the accuracy of DProf and show that DProf is able to give you strongly bounded, accurate analyses at a very moderate increase in execution cost for the timestamp synchronization.
We have time for some questions. Yeah, come up. So I have a quick question.
Sure.
I want to understand if DCause is doing the sort of thing that Cause does, where it conducts a bunch of experiments, what they call virtual speed up, so they slow down the rest of the program.
Yeah, so for anybody who's familiar with the original implementation of Cause, it's a quite sophisticated, it uses some quite sophisticated techniques that are only applicable to shared memory parallel programs. So to answer your question, no, this does not operate in the same way that DCause operates. We simply started from the point of, okay, if we wanted to ask similar types of questions, but not trying to replicate the implementation details of Cause. So yeah.
Hey, thanks for your talk. I didn't see a whole lot of discussion of networking in your slides. There was some mention in the paper. I was just wondering about, networks are complicated. They have variance. How do you account for the fact that there's variability in the latency of sending messages?
Okay, so during the timestamp synchronization, or during the calculation of the frequencies and zeros, actually, what we do is we make sure that we perform those calculations using UDP, and if there is, basically what happened was we started off doing this with TCP, and we noticed that we were getting some inaccuracies in it that were due to the result of TCP's auto, resending, like when it loses packets along the network, it'll automatically resend it, and that caused basically what was a virtual increase in the round trip time. And so to avoid things like that, what we do is we use UDP, and we have our own retry mechanism that takes the starting timestamp again, as opposed to using that same one. So yeah, does that help answer your question a little bit?
A little bit, but UDP doesn't solve the variability problem, right? Like you still have congestion, you could still have, all sorts of scheduling on the local machine that might, interfere with that latency.
Right, so which...
But I guess you use UDP as the principal mechanism for solving that, for lowering the latency between two machines.
Yes. Yeah, but it's important to note that that only comes up during the calculation of the zeros, during that specific part. So
what if that calculation is wrong, for example? What if it's off by?
Then you'll see an increase in your error bounds. So when you do your analysis, the bounds will be wider. So instead of like the 1% that you saw there, it may be like 5%, for instance, if you have really bad zeros that were affected by like, for instance, if you took them during a time where you were running another distributed program that was heavily using the network.
Okay, thanks.
Okay, let's have one last question from Emory.
Right, so I have a question. So while watching your talk, it felt very reminiscent of the way Spanner works and the true time algorithm that's used at Google.
Yeah.
So I wondered if you could speak to that and describe the core differences. Obviously, there's no atomic clocks in your setting.
Right. Yeah. So so let me start off by saying that I'm not super familiar with Spanner. At the time I did this research, I did look into it, and I was more familiar with it then, and it's my knowledge about it has since lapsed. But I think the primary difference between the two techniques is that, and correct me if I'm wrong here, but I think Spanner requires like some specific hardware help. Like it uses
Yeah, so Spanner, I mean, it uses to really minimize the bounds, rather than relying on on-chip timestamp counters. It literally uses atomic clocks deployed at the servers.
Yeah.
But I mean, the technique in general is all about bounding times, and everybody, even though they're atomic clocks, the atomic clocks are also not truly synchronized because of relativity.
Right.
And so they use the same sort of kind of general approach of saying, well, we know about message transmission, and we've measured these things, and we keep track of drift, and then we have some guarantees because of ordering and so on and so forth.
Yeah. So we don't do any kind of attempts to kind of measure the drift and account for that in the bounds, because we wanted them to be like very strict bounds. In other words, if we estimated the drift, then there would be some error introduced there that we wouldn't know the magnitude of. Does that make sense?
I mean, okay, yeah. I mean, I think that they are very careful to make sure that they keep their bounds in sort of guarantees as well. But anyway, we should probably
like
take
I
this
said,
offline.
I'm not
Yeah, sounds
super
good.
familiar with
All right, thanks.
Great. All right, let's thank the speaker once more.
Thank you.